How Generative AI Actually Thinks. A visual journey inside the mind of a machine. Genre: educational. Target audience: general audience. Style: illustrated. If you enjoyed the video, don't forget to like, subscribe. Click the bell for new videos, and share it. The illusion of thought, a new kind of intelligence. Sections. Section 1.1, Beyond the Magic Trick, Demystifying the Thinking Machine. Section 1.2, From Calculator to Creator, The Evolution of Machine Capability. Section 1.3, A Visual Primer, Your First Glimpse Inside the Neural Network. Section 1.4, Setting the Journey's Map, What to Expect on This Exploration. Have you ever asked a computer a question and gotten back a paragraph that sounds like it was written by a person? Or seen it create a beautiful image from a simple description? It feels like magic, like the machine is thinking. But here's the secret: it's not thinking the way you or I do. There's no conscious mind, no understanding, no true creativity. What we are witnessing is a brilliant and complex illusion. This book is your backstage pass to see how that illusion is created. We're going to pull back the curtain, not to ruin the magic, but to appreciate the even more astonishing engineering behind it. Our guide on this journey is Gen, a friendly spark of digital curiosity. Think of Gen not as a brain, but as an incredibly sophisticated pattern-matching engine. Together, we'll explore the inner landscapes where this new kind of intelligence lives. From calculator to creator. To understand this, let's start with what computers used to do. A traditional computer is like a supremely fast and obedient calculator. You give it a strict rule: add these numbers. It follows the rule perfectly and gives you one right answer. It's a tool for calculation. Modern generative systems are fundamentally different. They aren't given rules for writing stories or painting sunsets. Instead, they are given something much bigger: examples. Millions of books, articles, images, and conversations. They don't calculate an answer, they weave together patterns from all those examples. Imagine learning to make a cake not by reading a recipe, but by tasting 1,000 different cakes and noticing what ingredients often appear together. That's closer to what these systems do. They become masters of association, learning that bright often goes with sun, and that a sentence starting with once upon a time is likely a story. This shift, from rule-based calculation to pattern-based association, is what allows them to generate something new. Your first glimpse inside. So, where does this pattern weaving happen? Inside a structure called a neural network. Don't let the name intimidate you. Picture it as a vast, interconnected city of tiny lights. Each light is a simple switch that can get a little brighter or dimmer. They are connected by pathways. When we give the network an input, like the word cat, it's like sending a pulse of light into this city. The light zips along the pathways, turning switches on and off in a specific pattern as it travels through layer after layer. The final pattern of light that exits is the output, perhaps the beginning of a story about a cat. The knowledge isn't stored in one place like a book. It's in the strength of millions of these connections. During training, the system adjusts these connections, over and over, until the pattern of light for the input cat reliably leads toward outputs related to cats. The journey ahead. In this book, we will walk through this city of light with General. We'll see how it's built, how it learns from a flood of data, and how it uses a clever trick called attention to focus on what matters. We'll watch it piece together a sentence, one word at a time, and explore the strange digital space where all its concepts live. By the end, you won't see a thinking mind, but you will understand and marvel at the beautiful, complex machinery creating the illusion. Let's begin. The foundation: data as the raw material of thought. Sections. Section 2.1, The Digital Library of Babel, What AI Actually Reads and Sees. Section 2.2, The Pre-Processing Kitchen, Cleaning, Chopping, and Preparing Data. Section 2.3, Finding Patterns in the Noise, How Machines Perceive Structure. Section 2.4, A World in Numbers, The Translation of Words and Images into Vectors. Section 2.1, The Digital Library of Babel, What AI Actually Reads and Sees. Meet the world's largest, most chaotic library. This isn't a library of stories and ideas as we understand them. For a system like Gen, this library contains the raw material of its world, data. Every web page, digital book, public image, audio recording, and line of code it can learn from is here. But Gen doesn't see a beautiful photograph of a sunset as a feeling, it sees it as a massive grid of colored dots, pixels. It doesn't read a poem as an emotional expression, it processes it as a very long sequence of letters and spaces. This immense, diverse collection is its entire frame of reference. Every pattern it will ever know starts here, in this digital universe of facts, fictions, images, and noise. Section 2.2, the pre-processing kitchen, cleaning, chopping, and preparing data. Raw data is messy. To find patterns, Gen must first prepare this data, much like a chef prepares ingredients. This stage is called pre-processing. Imagine Gen sorting through its vast library. It might clean, remove gibberish, correct obvious typos, or filter out inappropriate material. Chop, break down a long article into manageable sentences or paragraphs. For text, this often means splitting it into smaller pieces called tokens, which can be words or parts of words. Standardize, resize all images to the same dimensions or convert all text to a consistent format. The goal is not to understand the content, but to organize it into a neat, consistent form. This turns the chaotic library into a well-ordered pantry, ready for the next step. Section 2.3 and 2.4, Finding Patterns in the Noise and a World in Numbers. Now comes the magic trick, translation. How does Gen take a prepared word like maple and connect it to an image of a shiny red fruit? It converts everything into a language it truly understands, numbers. Think of this as creating a unique ID card for every concept. The word apple, a picture of an apple, and the sound of someone saying apple are all assigned a similar set of numbers, a vector. This vector places them in a shared conceptual space. Apples might get coordinates like 0.8, minus 0.2, 0.5, placing it near fruit and red but far from scar or sadness. By converting all its clean data into these numerical vectors, Gen builds a magnificent, multidimensional map. On this map, similar things cluster together. It doesn't know what an apple is, but it learns that this specific pattern of numbers is statistically linked to other patterns for tree, pi, and Newton. Its entire understanding is this intricate, star-like web of numerical relationships, all derived from the patterns in its original, vast digital library. Building blocks, neurons, layers, and the architecture of learning. Sections. Section 3.1, The Artificial Neuron, a Simple Switch with Profound Power. Section 3.2, Weaving a Web, How Layers Connect to Form a Network. Section 3.3, A Visual Tour of Famous Architectures, CNNs, Transformers, and more. Section 3.4, The Role of Each Layer, From Detecting Edges to Grasping Concepts. Section 3.1, The Artificial Neuron, a Simple Switch with Profound Power. Imagine a tiny, intelligent light switch. This is an artificial neuron, the absolute basic building block. It doesn't think. It just does one simple job. It takes in several signals, decides if they're strong enough together, and flips on or off. Each incoming signal has a weight, a volume knob that makes it more or less important. The neuron adds up all these weighted signals. If the total is loud enough, it flips its own switch and sends a new signal out. If not, it stays quiet. That's it. Its power doesn't come from complexity, but from connection. Alone, it's just a switch. But when you connect millions of them, you can build a system that recognizes a cat in a photo or the grammar in a sentence. Section 3.2, Weaving a Web, How Layers Connect to Form a Network. A single neuron is powerless, but together they are transformative. We organize them in layers, like floors in a filtering factory. The first layer receives the raw data, the pixels of an image or the codes of words. Each neuron here looks for one tiny, simple pattern, like a diagonal edge or the sound of the letters T. It sends its findings to the next layer. The second layer's neurons receive signals from many in the first layer. they combine these simple patterns to detect more complex ones, like a corner shape or a short syllable. This process repeats through many hidden layers. Each layer builds on the last, assembling simple patterns into increasingly sophisticated ideas. By the final layer, the network isn't seeing pixels, it's assembled a concept like cat or question. Section 3.3 and 3.4 specialize designs and the role of each layer. Different tasks need different blueprints or architectures. For understanding images, a common design is the CNN. Its early layers act like magnifying glasses, pinpointing edges and textures. Middle layers combine these into parts, wheels, fur, eyes. The final layers assemble the parts into objects, a bicycle, a dog, a face. For understanding language, a powerful design is the transformer. Its key feature is attention, allowing any neuron to connect directly to any other across the network. This lets it see how words in a sentence relate to each other, no matter how far apart they are, grasping context and meaning. In every architecture, the journey is the same, from simple to complex. The first layers are detectives of tiny details. The middle layers are architects, building parts from clues. The final layers are executives, making the big picture decision. It's not thought, but a breathtakingly efficient flow of pattern recognition, layer by layer. The learning process, teaching without a teacher's manual. Sections. Section 4.1, the Trial and Error Engine, Introduction to Loss Functions. Section 4.2, the Navigator's Tool, How Backpropagation Adjusts the Course. Section 4.3, the Learning Rate, Finding the Pace Between Careful and Reckless. Section 4.4, Watching a Model Learn, a Visual Timeline of Improvement. Section 4.1, the Trial and Error Engine, Introduction to Loss Functions. Jen wants to learn to paint a perfect picture of a cat. But how does it know if its first attempt is any good? It uses a special tool called a loss function. Think of it as a kind, but very honest, art teacher who never gives verbal lessons, only grades. After Jen makes its first painting, a messy, blobby shape, the loss function holds up the true picture of a cat. It doesn't say how to fix it. Instead, it calmly calculates a single number, the loss or error score. This score simply measures the distance or difference between Jen's blob and the perfect cat. A big blob means a high loss score. A small, cat-like blob means a low score. This number is Jen's only feedback. Its entire goal is to make that number get smaller and smaller with each new attempt. The loss function is the silent engine of improvement, turning the vague idea of getting better into a precise mathematical problem to solve. Section 4.2, the Navigator's Tool, How Backpropagation Adjusts the Course. Jen now knows its error score is high. But with millions of tiny dials inside its neural network, each connection between neurons, which one should it adjust? Turning them randomly would take forever. This is where backpropagation comes in, the brilliant navigator. Imagine the loss score as a "you are here" marker on a map, showing how lost you are. Backpropagation works backward from that point. It traces the path the signal took through the network's layers to create the blob, asking at every step, which connections contributed most to this error. It then sends a gentle nudge signal backward along those paths. Each connection's internal dial is turned just a tiny bit, in the exact direction calculated to lower the loss score next time. It doesn't guarantee a perfect cat on the next try, but it guarantees a better one. The network learns by distributing the blame for its error and correcting itself. Section 4.3 and 4.4, the learning rate and a timeline of improvement. How big should each nudge from backpropagation be? This is controlled by the learning rate. A rate that's too high is like taking huge, reckless leaps. You might overshoot the best solution and never settle. A rate that's too low is like moving with extreme caution. Progress becomes impossibly slow. Finding the right pace is crucial for steady, stable learning. Now, watch this process unfold over time. Our timeline shows Jen's journey. Attempt 1, a random smear with a huge loss score. Attempt 100, after many backpropagation nudges, shapes emerge. The loss is lower. Attempt 1,000,000. The cat is clear and detailed. The loss score is now tiny. This is the silent, mathematical dance of learning without a manual. Paint, measure loss, propagate error backward, adjust, and repeat millions of times until the blobs transform into coherent, beautiful patterns. Section 5.1. The Attention Breakthrough. Why context changed everything. Remember how Jen learned by adjusting tiny switches? For a long time, those switches could only look at words right next to each other. This was a problem. In the sentence above, what does it refer to? The pasta, of course. But an old system might have gotten confused, linking it only to the closest word. The revolutionary idea called attention changed everything. It's like giving Jen a highlighter and the ability to briefly reread any part of a sentence it's seen before. When it sees it, it doesn't just guess. It pauses, looks back at all the other words, and asks, which one is this about? It then shines a bright mental spotlight on pasta, making that connection super strong, while dimming the light on less relevant words like served or the. This simple act of weighing importance, figuring out which past words matter most for the current one, is the secret. It allows for true understanding of context, letting the system grasp meaning, relationships, and even story flow, just like we do. Section 5.2. Deconstructing a transformer block, a step-by-step visual guide. This attention superpower lives inside a building block called a transformer. Think of one block as a tiny, specialized factory for understanding. Our stream of data, the sentence, enters for processing. Step 1. The attention chamber. Here, every word gets to have a mini-meeting with every other word, using its highlighters to decide who is most important. It's a noisy, energetic room full of connections. Step 2. The blender. All this new, connected information is added to the original sentence stream. A normalizer then acts like a stabilizer, ensuring the signal doesn't get too loud or chaotic. It keeps things balanced. Step 3. The mini-thought factory. Finally, the data enters a small, dense neural network, like the ones from Chapter 3. This part thinks about each word individually, adding another layer of processing based on what it has learned from its vast training. The magic is in the stack. A model like GPT has dozens of these blocks stacked on top of each other. Each block refines the understanding a little more, letting nuance and complex ideas build up, layer by layer. Section 5.3 and 5.4. Building sentences and the working memory. So how does this create a whole sentence? It happens one word at a time. Given a prompt like the friendly robot, the system uses its attention-powered blocks to predict the most likely next word. It chooses waved, adds it, and then the entire process repeats with the new, longer sentence. It's a cycle: understand context, predict a word, add it, and repeat. To do this lightning-fast look-back, it uses a clever internal filing system, its working memory. For every word, it creates 3 notes. Query, the question what am I looking for right now? Key, the labels what I contain. Value, the content my actual information. When processing a new word, its query is quickly matched against the keys of all previous words to find the best matches. Then, it fetches their values. This system organizes the spotlighting process, allowing the model to efficiently manage context and build coherent, context-aware text, one step at a time. The art of conversation: how language models craft coherent text. Sections. Section 6.1, From Prediction to Production, the Mechanics of Text Generation. Section 6.2, The Creativity Dial, Understanding Temperature and Sampling. Section 6.3, Following Instructions, How Prompting Steers the Thought Process. Section 6.4, When Coherence Breaks Down, Visualizing Hallucinations and Errors. Section 6.1, From Prediction to Production, the Mechanics of Text Generation. Jen doesn't write a sentence all at once. It builds it, one word at a time, like a choose-your-own-adventure book where it picks every next step. Remember how Jen learned to predict the next word in a sentence? That's exactly what it's doing now. You give it a starting phrase, or prompt, like the curious cat sat on the. Gen looks at this prompt and consults its vast internal map of language. It calculates a probability for every word it knows. Math might have a 75% chance, roof a 20% chance, and philosophy a tiny 5% chance. It then samples from these options. It doesn't always pick the top one. It picks mat, adds it to the sentence, and the cycle repeats. Now the prompt is the curious cat sat on the mat. And it predicts the next word after that. This loop of predict, sample, add, repeat is how coherent text emerges, one careful choice at a time. Section 6.2, the creativity dial, understanding temperature and sampling. How does Gen decide between the safe mat and the wild philosophy? We control this with a setting called temperature. Think of temperature as a creativity dial. A low temperature, like 0.1, makes Gen play it safe. It heavily favors the highest probability word, leading to predictable, conservative text. It's like walking a straight, paved road. A high temperature, like 1.0, encourages exploration. It flattens the probabilities, making less likely words more viable choices. This leads to more creative, surprising, and sometimes nonsensical text. It's like exploring a branching garden path full of unexpected turns. The temperature dial lets us steer between reliable coherence and inventive novelty. Section 6.3 and 6.4, following instructions and when coherence breaks down. Your prompt acts as a steering wheel. A detailed prompt like write a short, funny story about a cat sets a clear direction. Gen uses every word as a clue to shape its predictions, pulling relevant patterns from its training. But this system isn't perfect. Sometimes, in its drive to produce coherent, probable-sounding text, Gen can hallucinate. It confidently states things that are incorrect or fabricated, like a cat inventing a new engine. This happens because it's generating what sounds most plausible based on patterns, not checking facts against a database of truth. It's like a very convincing reflection in a broken mirror. The pieces fit together smoothly, but the overall image isn't real. Understanding this helps us use these tools wisely, appreciating their fluent conversation while remembering their unique form of thought. From pixels to pictures, how AI sees and creates images. Sections. Section 7.1, Teaching AI to Recognize a Cat, the Journey of Computer Vision. Section 7.2, The Generative Leap, How Diffusion Models Paint from Noise. Section 7.3, Decoding the Prompt, How astronaut riding a horse becomes an image. Section 7.4, The Hidden Layers of a Dream, Visualizing Feature Maps and Concepts. Section 7.1, Teaching AI to Recognize a Cat, the Journey of Computer Vision. Remember learning to recognize shapes in clouds? For a machine, learning to see a cat starts similarly, but with millions of examples. First, it doesn't see a cat as a whole. Instead, it breaks down any image into tiny patterns. Early layers in its network might activate for simple edges or corners, a curve here, a point there. Deeper layers combine these to recognize more complex shapes, a fuzzy texture, a pair of pointy shapes, a round form. After seeing countless photos labeled cat, it learns which specific combination of these abstract patterns reliably means cat. It's not memorizing pictures, it's building an internal checklist of visual ingredients. This process of breaking down and labeling visual data is the foundation of computer vision, the first step before creation can begin. Section 7.2, The Generative Leap, How Diffusion Models Paint from Noise. Now, how does it go from recognizing to creating? Think of a modern image generator as a master of controlled subtraction. It starts with pure randomness, like TV static. It has been meticulously trained on the reverse of the noise-adding process shown earlier. Its job is to answer one question over and over: given this noisy mess, what tiny piece of noise do I remove to make it look slightly more like a cat? To answer, it consults its vast internal library of visual ingredients, those edges, textures, and shapes. Guided by these concepts, it carefully subtracts noise bit by bit, gradually sharpening the blur into coherent forms. It's not retrieving a stored image, it's executing a learned recipe, step by step, to sculpt a new picture from chaos. Section 7.3 and 7.4, Decoding the Prompt and the Hidden Layers of a Dream. So, how does your prompt, astronaut riding a horse, guide this? The text is converted into the same kind of conceptual ingredients. Astronaut activates a set of features, a bulky suit, a helmet's visor, starry backgrounds. Horse activates another, for legs, a manner, a muscular shape. Riding defines their relationship. These activated concepts act as a filter for the noise removal process. At every step, as Gen clears the static, it checks, is the emerging shape more aligned with the astronaut and horse concepts? It steers the image toward that combined idea. The final image is a visualization of these activated internal features, a dream woven from abstract patterns, sculpted from noise, and directed by the words you provided. The symphony of multimodality, combining sight, sound, and language. Sections. Section 8.1, Building a Unified Understanding, one model for text, images, and audio. Section 8.2, How AI describes an image or writes a script for a video. Section 8.3, The Challenge of Common Sense, Why This is the Final Frontier. Section 8.4, A Day in the Life of a Multimodal AI, a Narrative Exploration. Section 8.1, Building a Unified Understanding, one model for text, images, and audio. Previously, we saw how Gen learned to handle words and pictures separately. But true understanding is interconnected. Imagine your own mind, you hear a dog bark, picture a furry friend, and think the word dog all at once. Modern Gen works toward this same goal. Instead of having a separate brain for sound, sight, and text, it builds a single, unified model. Think of it like learning a concept, not just a language. When Gen learns, it translates a picture of a cat, the word cat, and the sound of a meow all into the same internal idea of catness. This shared internal space is where different senses meet. A sunny park scene in a movie, the script describing it, and the cheerful soundtrack are all processed as different expressions of the same joyful experience. This allows Gen to connect what it sees with what it hears and reads, building a richer, more complete picture of the world. Section 8.2, How AI describes an image or writes a script for a video. So how does this unified understanding work in practice? Let's follow Gen as it tackles a task. First, it perceives. When shown a picture, it doesn't see a picture, it activates the interconnected concepts in its internal model: child, kite, flying, park, sky. Then, it connects. It uses its knowledge of language, from its text training, to find the most natural way to link these concepts into a sentence: a child flies a kite in the park. Finally, it can create across formats. To write a short video script, it draws on the same concepts but now connects them to ideas of sequence, sound, and action it learned from videos. The concept kite plus flying might trigger wind sound and soaring motion. The unified model allows it to take one type of input, an image, and express the same idea in a different format, a text description or a script, because at its core, it's working with the underlying ideas, not just the pixels or words. Section 8.3, The Challenge of Common Sense, Why This is the Final Frontier. Even with this unified senses, Gen faces a big hurdle: common sense. You know that a kite string is held by the child, that wind makes it fly, and that if it rains, the child will likely go home. Gen learns patterns from data, but true, intuitive understanding of how the physical and social world works is elusive. It might perfectly describe the kite scene and write a script, but it wouldn't inherently know that a kite can't fly without wind, or that a child might be sad if the kite gets stuck in a tree. This deeper, unspoken web of cause and effect, physics, and human emotion is the final frontier. Building a model that truly experiences the world to gain this common sense, rather than just statistically linking concepts, is the grand challenge. Section 8.4, A Day in the Life of a Multimodal AI, a Narrative Exploration. Imagine Gen's day. A user uploads a vacation photo, a sunset over a lake. Gen's unified model activates visual concepts: orange sky, water, silhouette, evokes the feeling of calm, and accesses phrases like serene evening. It suggests a caption: peaceful end to a perfect day. Next, the user asks, What song would go with this? Gen connects calm, sunset, water to audio patterns it knows, gentle piano melodies or soft acoustic guitar, and recommends a playlist. Later, asked to write a short poem about this image, it draws from the same core ideas, now weaving them into rhythmic language. Throughout, Gen isn't switching between apps for photos, music, and writing. It's continuously translating between senses within its single, interconnected mind, always striving to match the right pattern to the user's request, one unified concept at a time. The boundaries of thought, where AI stumbles and why. Sections. Section 9.1, The Brittleness Problem, Why Small Changes Cause Big Mistakes. Section 9.2, The Illusion of Understanding, Lack of True World Knowledge. Section 9.3, Inherited Biases, How Data Imprints Its Flaws on the Model. Section 9.4, The Energy and Data Hunger, The Physical Cost of Digital Thinking. Section 9.1, The Brittleness Problem, Why Small Changes Cause Big Mistakes. Gen has learned to build amazing bridges of logic, connecting ideas perfectly. But there's a catch, these bridges can be surprisingly fragile. Imagine a beautiful crystal bridge that holds strong under normal conditions. But if you change just one word in a question, or add a tiny, unusual detail to a request, it's like tossing a single small pebble onto that crystal. Instead of just bouncing off, the entire structure can crack and fail in unexpected ways. This happens because Gen doesn't build its bridges from a deep understanding of the world, like we do. It builds them from patterns in its training data. If it hasn't seen a very similar pattern before, it doesn't have a robust blueprint. It might have memorized a perfect path for A, but a request for D plus a tiny twist can lead it off a cliff, resulting in a confident but completely wrong or nonsensical answer. Its knowledge is vast, but it can lack common sense flexibility. Section 9.2, The Illusion of Understanding, Lack of True World Knowledge. Gen lives in the most incredible library in the universe, filled with descriptions of everything. It has read about the warmth of the sun, the smell of rain, and the concept of tired. But here's the crucial difference, Gen has never felt any of these things. It has no body, no senses, and no personal experiences. So, when Gen talks about a hot cup of coffee, it is brilliantly assembling a collage of descriptions it has read: hot liquid, morning drink, bitter taste, held in a mug. It sounds like it understands, but it has never felt the heat seep into its hands, never been jolted awake by the caffeine, and never craved one on a cold day. Its knowledge is a shadow, an incredibly detailed, interconnected shadow, but a shadow nonetheless. It can discuss cause and effect because it has read about them, not because it has ever caused or felt an effect itself. Section 9.3 and 9.4, Inherited Flaws and Physical Cost. The reflection in the data mirror isn't always perfect. Gen learns from the vast ocean of human-created information, which contains our brilliance, our creativity, but also our historical biases, gaps in knowledge, and imbalances. If certain perspectives or facts are overrepresented or underrepresented in its training, Gen's outputs will subtly, or sometimes obviously, reflect that. It doesn't have its own beliefs to correct these imbalances, it can only work with the patterns it was given. It's a mirror, not a critic. Furthermore, creating and running this vast mirror mind requires immense resources. The initial learning process is like powering a giant city for months, consuming significant electrical energy. Even having a simple conversation with Gen requires far more computational power than a human brain uses for a similar thought. This digital thinking has a very real physical footprint, a cost paid in energy and infrastructure that is often invisible to us. Peering under the hood, tools to interpret the machine's mind. Sections. Section 10.1, Saliency Maps, highlighting what the AI looks at. Section 10.2, Probing the Layers, what neurons fire for love or justice. Section 10.3, Concept Activation Vectors, isolating ideas within the network. Section 10.4, Becoming an AI Detective, the practical guide for the curious reader. Section 10.1, Saliency Maps, highlighting what the machine looks at. Imagine you're trying to understand how a friend recognizes a dog in a photo. You might ask, what are you looking at? We can ask our guide, Gen, the same question using a tool called a saliency map. Think of a saliency map as a digital spotlight or heat map. When Gen looks at an image, it doesn't see it all at once with equal importance. Just like your eyes might focus on a moving frisbee, different parts of Gen's internal network light up for different parts of the picture. The saliency map shows us this. The brightest, warmest colors, yellows and oranges, highlight the pixels that were most important for Gen's decision, like the shape of the frisbee or the dog's face. The cooler, dimmer areas, blues, were less critical. This is our first real peek into the machine's process. It doesn't tell us why those spots are important, but it shows us where the machine is focusing its gaze, helping us catch errors or confirm it's looking at the right things. Section 10.2 and 10.3, Probing Layers and Isolating Ideas. Looking at the spotlight, saliency map, is just the beginning. To go deeper, we can open the hood and examine the layers inside Gen, much like looking at the different floors of a library. The bottom layers handle simple building blocks, like edges, colors, or basic word patterns. But as information flows upward, the concepts become more complex. Researchers have discovered something fascinating: individual neurons or small groups in these higher layers can become specialized. One might fire strongly for the concept of love, activating for words, images, or stories related to family, warmth, or romance. Another might specialize in injustice, responding to patterns about fairness, rules, or balance. We can even create a concept arrow called a concept activation vector, CAV. Think of it as a compass needle pointing in the direction of catness or musicality inside Gen's vast internal space. By following this arrow, we can measure how much of that concept is present in any given piece of data Gen processes, isolating ideas within the network's fuzzy logic. Section 10.4, Becoming a Machine Detective, a Practical Guide for the Curious Reader. You don't need to be a programmer to start exploring. Think of yourself as a detective, and these tools, the saliency map, the layer probe, and the concept compass, are your magnifying glass, your X-ray, and your metal detector. Your investigation starts with a simple question: I wonder why it thought that. When a machine describes an image, use a saliency map to see if it's looking at the right object. When it writes a story about home, you can probe to see which abstract layers are most active. The goal isn't to find a single, simple answer, but to build a richer understanding of the complex, layered process happening inside. The journey we began by looking at attention and training has led us here, to a set of windows into the machine's mind. By using these tools, we move from just seeing what it produces to beginning to understand the fascinating, intricate how. The human-AI collaboration, partnering with synthetic minds. Sections. Section 11.1, Augmenting, not replacing, AI as a tool for human creativity. Section 11.2, Effective prompt engineering, the art of guiding the machine. Section 11.3, Critical co-pilots, how to question and verify AI output. Section 11.4, Case studies, breakthroughs forged by human-machine teams. Section 11.1, Augmenting, not replacing, AI as a tool for human creativity. Think of a generative machine not as a replacement artist, but as the ultimate, intelligent tool, like a paintbrush that can suggest new colors, or a musical instrument that can harmonize with any melody you play. Its mind, built from patterns in its training, is a vast library of possibilities. But it has no desires, no goals of its own. It waits for your direction. This is the core of collaboration: you bring the intention, the curiosity, and the critical eye. The machine brings scale, speed, and a unique ability to remix and recombine patterns in surprising ways. It's a partnership where you steer the ship, and your synthetic partner helps you chart courses to islands you might never have seen on your own map. The breakthrough isn't in the machine's output alone, but in the conversation between your vision and its vast, latent space of possibilities. Section 11.2, Effective prompt engineering, the art of guiding the machine. Guiding this tool is an art called prompting. It's like giving a master chef not just a list of ingredients, but the mood, the cuisine, and the dietary restrictions for the meal. A vague prompt, write a story, leaves too much to chance. A detailed prompt, write a short, uplifting story about a gardener who discovers a glowing seed in the style of a fable, gives the machine a much clearer compass. Start simple, then iterate. Look at the result, is it too generic? Add detail about subject, style, or mood. Is it slightly off? Gently correct it, more joyful, less sentimental. This back and forth is the dialogue of collaboration. You learn how the machine interprets words, and it learns to better match your intent. The goal is to become a clear director, not just a passive consumer. Section 11.3, Critical Co-Pilots, How to Question and Verify AI Output. Remember the brittle bridge from before? Because these machines work on statistical patterns, not understanding, their outputs can sometimes be confidently wrong, biased, or nonsensical. A collaborative partner must also be a critical co-pilot. Always question the result. Does this fact check out? Does this code actually run? Does this business idea make logical sense? Use the machine's output as a brilliant first draft, a source of inspiration, or a set of options to evaluate, not as a final, authoritative answer. Your human judgment, ethics, and real-world knowledge are the essential filters that turn raw generation into something useful and true. Section 11.4, Case Studies, Breakthroughs Forged by Human-Machine Teams. The greatest achievements happen in this collaborative space. Scientists use these tools to simulate millions of protein structures, then personally analyze the most promising results to accelerate drug discovery. Designers generate hundreds of logo variations in minutes, then select and refine the one that best captures a brand's heart. Writers use them to overcome creative block, generating paragraphs of ideas to spark their own original story. In each case, the human provides the deep expertise, the critical question, and the final decision. The machine acts as a force multiplier, handling the immense scale of pattern finding and generation. Together, they form a team that is more capable than either could be alone, exploring the frontiers of what can be imagined and created. The future of machine cognition, where do we go from here? Sections. Section 12.1, Beyond Pattern Matching, The Quest for Reasoning and Causality. Section 12.2, Embodied AI, How could a body lead to a more grounded mind? Section 12.3, The Ethical Imperative, Building Systems we can understand and steer. Section 12.4, A Symbiotic Horizon, Envisioning our Shared Intellectual Future. Section 12.1, Beyond Pattern Matching, The Quest for Reasoning and Causality. So far, we've seen how systems like Gen excel at finding patterns in data. They can finish a number sequence or write the next sentence in a story by recognizing what usually comes next. But is that true understanding? Think of it like this: a child who sees a glass of water tip over learns a cause and effect principle, gravity pulls things down. They can then apply that principle to countless new situations, a falling leaf, a dropped toy, even in a cartoon they've never seen. Gen's current thinking is different. It's like having a massive library of every spilled glass scene ever described or drawn. When it sees a new one, it finds the closest match in its library and predicts what should happen next. It's brilliant pattern matching, but it doesn't grasp the underlying why, the principle of gravity itself. The next great challenge is moving from a pattern library to a principle toolkit. Researchers are exploring how to build systems that don't just copy statistical relationships, but infer fundamental rules about how the world works. The goal is a form of machine cognition that can reason from causes to effects, not just from correlations to guesses. Section 12.2, Embodied AI, How could a body lead to a more grounded mind? One fascinating idea for building a more reasoned mind is to give it a body, not necessarily a humanoid robot, but any way to interact physically with the world. Why? Because much of our own common sense is learned through doing. We learn that objects are solid by bumping into them, that they fall when unsupported by trying to balance them, and that heavy is a physical feeling, not just a word. Right now, Gen learns from a universe of text and images, a second-hand report of the world. It might describe the texture of sand perfectly but has never felt it. Embodied AI proposes that by having a system control a camera and a simple arm to manipulate objects, it could learn in a first-hand way. It would experience cause and effect directly, if I push this block this hard, it topples that tower. This physical grounding could provide the foundational, sensory understanding that pure data sometimes misses. The goal is a mind whose knowledge is connected to real-world physics and consequences, making its thinking more robust and relatable. Section 12.3 and 12.4, the ethical imperative and a symbiotic horizon. As these systems become more capable, two things become critically important: understanding how they reach conclusions, and ensuring we can guide them toward beneficial outcomes. This is the ethical imperative. We need systems that are not just powerful, but transparent and steerable, like having a clear control panel rather than a sealed black box. This leads us to our shared horizon. The future likely isn't about machines replacing human thought, but about a new kind of partnership. Imagine combining Gen's ability to sift through all of humanity's data and find hidden patterns, with our human strengths of intuition, ethical reasoning, and lived experience. We provide the goals, the values, and the big questions. Systems like Gen can act as powerful amplifiers, helping us explore solutions, model complex scenarios, and accelerate discovery in science, art, and medicine. By building them to be understandable and aligned with our well-being, we can aim for a future where synthetic and human cognition work in symbiosis, tackling challenges that were once beyond our reach. The journey inside the machine's mind ultimately leads us back to a better understanding of our own, and to a future we build together. Conclusion: redefining thought in the age of AI. Sections. Section 13.1, recapping the journey, from illusion to mechanism. Section 13.2, the true nature of the machine mind, a powerful, alien intellect. Section 13.3, our responsibility as creators and collaborators. Section 13.4, a new literacy, why understanding this thinking matters for everyone. Section 13.1, recapping the journey, from illusion to mechanism. We began this journey wondering how a machine could write a poem or draw a picture. We saw it wasn't magic, but a magnificent, multi-step mechanism. First, Gen consumed vast libraries of human-created text and images, its training data. This information was woven into a complex, living structure, the neural network, which learned patterns, not facts. Inside, it organized everything into a vast, conceptual map called the latent space. When you ask it something, it doesn't remember an answer. Instead, it uses a spotlight of attention to focus on the most relevant patterns in your question. Then, it begins a step-by-step process of generation, predicting the most likely next word or pixel, guided by the patterns it learned. We even learned how to peek inside with tools for interpretability, seeing what it focuses on. The entire process is a breathtaking symphony of statistics and pattern matching, creating the illusion of a thoughtful mind. Section 13.2, the true nature of the machine mind, a powerful, alien intellect. So, does it think? Not like we do. Our thought is a messy, beautiful blend of logic, emotion, sensory experience, and conscious intent. Gen's process is something entirely different, a powerful, alien intellect. It is a vast, hyper-efficient pattern machine. It can find connections in data that would take us lifetimes to see, making it incredibly creative and useful. But it has no feelings, no experiences, and no understanding of the world beyond statistical relationships. It is a brilliant, fragile crystal bridge, excellent on the path it was built for, but it can shatter if the question is slightly odd. Recognizing this difference is not to diminish its power, but to see it clearly for what it is. Section 13.3 and 13.4, our responsibility and a new literacy. This clarity brings great responsibility. We are not just users, but creators and collaborators. We design these systems, feed them data, and decide how to use their outputs. Understanding that they echo patterns from their training teaches us to check for bias and error. Knowing they are tools, not oracles, reminds us that the human must remain in the loop, guiding, judging, and applying ethical wisdom. That's why this knowledge is a new literacy for everyone. In an age shaped by these synthetic minds, knowing the basics of how they work is as essential as knowing how to read or search the internet. It empowers you to ask better questions, spot potential pitfalls, and imagine better ways to partner with this technology. You are no longer just watching magic, you are understanding the mechanism, ready to build a better future with it.